this is the question that this fellow asked. Okay, he said, when I rub my hair into a balloon, why does my hair stand up? Well, lucky you, some people don't have hair. But that's the wrong answer. Okay, yeah. Standard science says it's the electrons being knocked off from the balloon. Yeah. So without ions, how does that work? So yeah, if you rub a balloon or you rub maybe a comb or whatever, and you can pick up some little piece of paper, some confetti, right? Okay, so you can do the experiment at home. It's also done by countless people on the internet, right? So you can just look it up, YouTube, and find out that if you just rub something like that's made out of plastic, you can pick up things. There's what they call static electricity. And what we're going to argue today is that it's got nothing to do with static electricity, especially what this fellow said there, representing the establishment, that it's the donation of electrons to the other side, and now you have a negative pole here and a positive over here, and that creates the attraction. Yeah? By what mechanism? Negative attracts positive, North Pole attracts South Pole. What is it? You know, what's the mechanism? That's what we want to know. We want to understand the mechanism. We're mechanics. We're really mechanics. Scientific mechanics. Physics mechanics. Okay, so I have to begin. I'm going to go slowly on this because it's a loaded question whether he knows it or not. Okay, so let's go slowly. Here's our hydrogen atom, the one we propose. Okay, and it looks like that monster there. Okay, so what do we have there? We have all the ropes from every atom in the universe converging upon our atom. And by the way, that's a picture created by a fellow by the name of Dan. I'm not going to give his last name. I have no authority to do so. I had another fellow named Dave. He gave us the 2D version. This is the 3D version. And I really thank him, and has helped me a lot to be able to convey the theory. So thank you, Dan. You know who you are. So this is our atom. Okay, it's a 3D version of our atom. That's what it looks like. One thread goes through the center of the atom and creates that star-like, urchin-like entity there. And it's encapsulated by what we call the electron shell or an electron membrane or electron balloon. Any of those is just fine. Okay? So that's our atom. And that's the one we're going to be working with. Do you believe in that atom? We don't care. We're here to explain to you the model. You take it with you, sleep on it, reach your own conclusions. Here we only present, what we're proposing. Okay, so that's our atom. So far so good. That's so easy. We're done, right? Not so fast. We have a problem there. Okay, and here let me tell you what the problem is. Let's go to the next atom, and that's helium, right? And like on the periodic table, you go from hydrogen. The next one is helium. It takes 4 hydrogen atoms, right? Because you have to compress them inside the sun, naturally, right? To make a helium atom, because it's got 2 neutrons and 2 protons aside from 2 electrons, right? And so here we have it. We're going to try to make a helium atom with all this, and I put a little proton star in there. Okay, you can see that tiny light blue point there. Okay, I put it in there just like that. Don't worry about the actual thing out there. What I'm trying to show here, that it's got 2 protons. Remember, the proton is that part in the center where all the threads, not ropes, threads crisscross. The ropes are always outside the atom. Inside the atom, you only have threads. Okay, so you have the threads going through there, right? And we have another star in there, and we'll call it 2 protons. But we're missing something. What are we missing? Well, we're missing 2 neutrons, right? And so what is a neutron? Well, neutron is a cross point of ropes, not of threads, but of ropes. Not of threads, but of ropes. And people sometimes don't understand the difference. They talk about ropes when they mean threads, and they talk about threads when they mean ropes. So keep those 2 separate. Ropes are not threads. Threads are not ropes. Okay? It takes 2 threads to make a rope. They have to be twined. Then you can see a rope. Okay, so a cross point of ropes out there in the universe is what we call a neutron. And so we're going to put them in there. So we have two protons, right? The one in the center that was there, the other proton that we put in there, and two neutrons. Okay, so that's what we have in there. But we're still not done because so far we only have one shell. So where's the other electron shell? I mean, it's got to be a shell, right? Or you would think so at least. So we're still missing something here. Okay, we're still missing something. And let's find out if we can modify this so that we can incorporate the electron, the second electron in there. Electron membrane, right? The ball that encapsulates it. So we're going to conceptualize it like this. You can see now it's thicker on the outside, right? The shell. And I'm suggesting, my proposal, right, is that there is a separation between the two shells. A very tiny separation there, but there is a separation. So I don't think they're touching, the two shells are touching. There is a separation, but it was very hard to kind of illustrate that. If I would have separated too much, it would have sounded like what I'm going to show you later on. And so it would have been a little confusing. All I just want to say verbally, right, is that the shells are not touching exactly, right? There's a space between them, okay? So we have one shell on top of another shell. Now we have our two electrons, okay? Electron shells, right? Electron membranes, electron balloons, and now we can show here the difference between them. You can see the one on the right has the two shells, whereas the one on the left only has one shell. Okay, so the one on the left is your standard hydrogen atom. The one on the right is the one we're going to use to make the hydrogen atom, right? Okay, so here it is. We're going to put two protons in there. Remember, it's a thicker shell because it's one shell encapsulating another shell. And we're going to put a second proton in there. We have now two protons in there. What are we missing? The neutrons, right? Always those damn neutrons. Okay, so here we're going to put two neutrons in there. Okay, we got that? Okay, so we have now our hydrogen atom. Our helium atom. What is it? A double-shelled electron shell, right? Encapsulating two proton stars and two neutrons, which are cross points of ropes, not of threads, but of ropes. The protons are of threads, the neutrons are of ropes. Okay? That's our model for the helium atom. Okay? Okay, I hope people can visualize that, at least what we're proposing. Do you believe in it? Even I don't believe in it. So please don't believe. We're here to understand, not to believe. Okay, and let's move on to lithium now, the next atom. So we have hydrogen, helium. Now we're going to go to lithium, right? And lithium has 3 protons. And the typical isotope is not 3 neutrons, but 4 neutrons, okay? So just keep that in mind. Okay, so here now you can see how they're, one is encapsulated within the other. But here we're talking about something different. There's a bigger separation between the 1s orbital, which is the one on the inside, and the 1s on the inside, the 2s on the outside, S2, right? The S2 on the outside. The one on the inside, you can see, is thicker, right? Because it's got 2 electrons in there, right? The one on the outside only has 1 shell, okay, so far. Okay, so I just want you to see what we're doing here. We have 2 shells on the other side, one nested inside the other one. There's a tiny separation between them, but both of those are widely separated from the one that encapsulates both of them. Okay, that's what I'm trying to show there. Okay, that's our proposal. Do you believe in it? I don't know if you do or not. I don't believe in it, so why should you, right? And here we put 2 protons. We start there. Okay, so now we have our protons in there. Okay, 2 protons. 2 more protons. In other words, we have the original one and 2 more in there. Let's not worry right now on how that really is inside there. Let's just put them in there by force. We have to have 3 protons in there. There you have 3 protons. The main one in the center and 2 others, right? What are we missing? Our good old neutrons. There's 4 of them for the most popular, the most common isotope of lithium. Okay, so let's keep that in mind. Okay, there we have our 4 neutrons, okay, next to the protons. That's our proposal, okay? And so that's our lithium, but you can see how this is getting complicated. We're at element number 3. Just take it to element 92. You got to go through all these, S, what is it, the 2S or S2. You got to go through the D, the F, the G orbitals, P also, right? S, P, D, F, G, right? You go through all these orbitals, and it gets quite complicated. They also have different shapes, and you have to think of them as balloons. You've seen the clowns when they work with balloons out there and they make all different shapes. That's what the atomic world is like. It's just a bunch of balloons of different shapes, and they have to take those shapes. The bigger they are, the P, the D, the F, the G. Why? Because they don't fit. A certain spot is taken by the P, so the D cannot use that same spot, so it takes another spot, and then when comes the F, it's got to take another spot. Just trying to tie balloons together, and you'll find out that you cannot have a full circular, spherical balloon. It's going to have all these different shapes because one balloon interferes in the spot where another one is coming in. And so that's why they line up that way, and that's, I think, explains a lot of what we have in chemistry, where we have all these balloons in different shapes, with all these different levels. That's what we're trying to show here. We think it's balloon physics. That's what we'll call this chemistry, these different configurations of the atoms. Okay, so now let's get closer to the question this fellow asked. Let's start working on that a little bit. I showed the other day the covalent bond, and here I'm going to show it only as an S orbital with a p orbital. Okay, this is arbitrary. We just want to show the mechanism. What is the mechanism? Why do we have a covalent bond? Well, you have the s orbital moving in the same direction as the p orbital, and as one comes down, the other one comes up, and that's why they're attached to each other, and we have a strong, what is called covalent bond. Okay, and again, just an example here, we could have two S there's, we could have two P's, whatever, but here we put an S with a P. Okay, that's just an example. Okay, so that's the covalent bond according to the rope model. Okay, that's what we're proposing. You're welcome to criticize it, etc., etc. Okay, now here we're going to show the ionic bond. But what is the ionic bond? We're saying that somehow, right, because you stimulated an atom, suddenly one thread comes out. And I really think it's more than one thread. I think it's a bunch of threads. But the threads come out, and they're spinning around the atom. Okay, so let me show you first that the thread comes out. Looks like that. I just put one thread. You can imagine this being many threads. Okay, so here let me show you this. Okay, so it could be many threads coming out. Okay, so either one of those. Okay, again, these are just proposals. This is what we think is happening in there. Okay. Okay, so what happens? How do you create an ionic bond, not a covalent bond? Covalent bond was shell with shell, meshed with shell, and the threads are moving in the same direction for them to be attached, for them to have attraction. And only if they go in opposite direction do they push each other away, but then another atom gets them over there where they go in the same direction. Remember, you have billions of atoms in a tiny, tiny, small space. You have all these atoms going in every direction. When they catch someone that's going in the same direction, they get attached, and that's it. Okay, that's the model we're proposing for chemistry bonding. Okay, bonding, real bonding, like physical bonding, not with words, with fields and energy and whatever nonsense. Okay, so here we have our proposal. What the basic notion here, and I'm going to see it as a simple rotation of an atom. That's what we're saying is happening. What happens when two of these meet? Well, it looks more like that. And you can see as one comes down, the other one's coming up. Why? Because they're both moving in the same direction. That's what we're trying to show here. Okay, so that's where the attachment between two atoms occurs, because in an ionic bond. Why? Because it's not It's not a strong bond as the shell because the shell is merged with the other shell. Here we only have the threads that have come out loose because you stimulated them somehow. So this is what we call ionization. Okay, ionization and attachment in what we call an ionic bond. Okay, hopefully the images give you an idea what we're proposing here. Okay, we're just trying to get you to understand. And again, we distinguish that from the covalent bond, which is that one. Okay, so that is our covalent bond, shell with shell. The other one is just a few threads. That's my proposal. I don't know if it's one thread. I think it's many threads that are coming out because you stimulated that atom, and so they're spinning at great speeds. One is coming down, the other one's coming up. So they attach to each other in an ionic bond, which means they're loosely attached to each other compared to a covalent bond which involves the entire shell. Okay? That's our proposal. Okay, so now, once again, let's get back to the question this fellow answered. I'm sorry I got to give this introduction because I need to take you step by step to the question he asked, which is the why does he comb his hair and pick up papers with it, right? That's the question we're trying to answer. Okay, so here's the official version of that. We're going to have a coat, and we're going to rub a balloon against the coat, and we're going to create what they call static electricity. Okay? What is static electricity? Static electricity says that one of the objects picks up or erases, you could say, any way you want to look at it, picks up all the electron charges from the other guy, meaning leaves them with a positive charge, whatever that is, right? A bunch of numbers. And because one is negatively charged, the other one is positively charged, then one attracts the other. By what mechanism? By magic. It's called magic, black magic. Okay, it's action at a distance. We don't know how it is. We put the word field in there and get away with it, and nobody asks questions. That's the way it's done. Okay, so here we have it. Okay, we have a coat. We're going to rub the balloon against it. Okay, they have charges, whatever those are. It picks up all the electron charges. The balloon picks up all the electron charges, leaves it positively charged, the coat, and you see the negative charges on the balloon, and that's why the coat later on attracts the balloon. Okay, let's see it one more time here. Okay, we have a balloon and a coat. They both have normal charges, positive and negatives, right? We're going to rub the balloon. By doing so, it kind of picks up all the electron charges from the coat, takes it with it, becomes negatively charged, okay? And that's the reason it's attracted, by magic. It's attracted because it's got a potential, it's got a whatever they want to call it, right? And this is a problem. This is a problem because we have no mechanism. They just say, look, one object took the electron charges from the other. Electrons, right? They took all the electrons. Those are negative. I don't know why they're negative. They're like women, maybe men are positive, women are negative. Is that what it is? That's because we men were in charge of physics before the women were. I don't know. But maybe it's female, male. I don't know. The question is that you have all these negative charges, right? And it's negatively charged. It's attracted to the positive charge. By what mechanism? We'll never figure it out. It's just math. Okay? It is so. We have the equation to prove it. Okay? That's all they have. And so here we have the problem with that. One of the problems with that is that the electron is a bead. Okay, so here it is. This is, I think, from the Wikipedia, and it says the following. A second here. So electrons do not orbit a nucleus in the manner of a planet orbiting a star, but instead exist as standing waves. So the electron is not a little particle; it's a wave, right? And I guess they don't understand the difference between a ball and a wave. And there you see a standing wave on the right-hand side and a ball on the left-hand side. How come they can't tell the difference? I mean, you would think this is baby stuff that should have been covered in kindergarten. And yeah, they have these mishmash. They have a language there that does not clarify, what the electron is. Is it a wave or is it a particle? Is it a discrete little ball or not? And you'll never figure it out. And so the problem there says they do not orbit and instead exist as standing waves. No, exist is wrongfully used. Exist requires location, and location is a static concept. You see it at the bottom there in the Universal movie. All the static concepts are concentrated in a single frame of the film. So that's God's film there of the entire universe. One frame contains location only. Location static concept. What do we have? Distance from one atom to all other atoms in the universe. In a single frame, which you see on the right-hand side there, that's everything had better be standing still. So you cannot say that they exist as standing waves. No, they can't, because a standing wave is something in motion, whereas whatever an electron is, it better be static. You should be able to take a snapshot of it with God's camera, meaning nothing moves, right? And so the electrons are never in a single point location. They had better be. They had better be in a single point at some point in time when you take the snapshot. When God takes his snapshot, he cannot say, oh, but it's moving within my single frame. It can't. There's a problem there. And again, the problem with mathematical physics is it's a dynamic discipline, language, right? And so everything has to be in motion in mathematics. Otherwise, the entire mathematical world is dead. So they don't understand static concepts. They have to. An equation represents a dynamic concept. There is no equation that represents something static, even in geometry. Because in geometry, what it is an itinerary. You do not have a cube. What you have an itinerary around the cube, or a perimeter, or the sides, or whatever. You have a trajectory throughout this object, and that's what they put down as the equation. So, like, earlier I talked about the sphere, 4 pi r cubed over 3. Is that a static concept? No, it's a dynamic concept. What you're doing is an itinerary through the sphere, and you came up with 4 pi r cubed over 3. Now you have the equation for your itinerary. You just have to, replace sometimes the variables in there with numbers. Okay, so here we have, that was the wave version. Now here's the particle version, because, they never resolved this. Particle-like properties of the electron, right? Number of electrons orbiting a nucleus can be only an integer. So by that they're saying it's got to be like a little ball, a little point, right? Because we can specify it with a single number, right? So it's got to be an integer. Electrons jump between orbitals like particles. So if they jump between orbitals like particles, is the electron a wave or a particle? How can it be both? Again, they've never resolved this. And this is not an issue of going to the lab, because you're not going to observe, using your eyes. You're not going to be able to touch using your hands. This is something you do in your office. You look up, a girl for inspiration, and you visualize. You try to imagine what Mother Nature could be doing in that secret world of hers. You got to conceptualize. That's a theory. You cannot come up and say, oh, I went to the lab and observed. What are you going to observe? You can't observe an electron. You can't observe light, the mediator of light. You can't observe the mediator of gravity. So observation, tests, using your hands, tangibility, none of that has any bearing on the question we're asking. The question we're asking has to do with theory, with conceptualizing only. And then you have electrons retain particle-like properties. And you go, each wave state has the same electric charge as its electron particle, whatever that is. Because again, they're talking about math, and they say it's got a single charge, like 1.6 times 10 to the minus 19 coulombs, the value of the unit charge, right? Each wave state has a single discrete, spin. So they spin, but they don't spin, because spin is not spin like a top. It spins, whatever that is. So you have a zero-dimensional, or a particle that has no volume, essentially. And they say it spins. Well, I've never seen a zero-dimensional anything spin. But assuming it's got a little size, a minimum size, fine. Okay, does it spin? Now they say we call it spin, but that's only to mislead you, because they don't know what spin is. But then they always illustrate it as spinning like a top. And so again, we have the wave. Does the wave spin like, sideways, or what are they talking about? What's spinning? Is it the ball? I mean, how do they know it spins? Well, it's just a number. Spin is a number. They call it spin to mislead people. They illustrate it as spinning, as a spinning top, but then they, at the end of the presentation, they say, "Oh, by the way, we weren't talking about spinning." So what were you talking about? You weren't talking about spin. Why did you use the word spin? Oh, because it's tradition. Okay, so here we get down to the orbitals. Okay, and that's what you find for the orbitals. You have the S, the P's, the D's, the FG's, and so on. And what you have is, you can see they have different shapes, okay, all these orbitals. And this is what they mapped using Heisenberg's equation, essentially. I'm sorry, Schrodinger's equation, okay? So that gives them an idea of what could be in that world of, micro world of Mother Nature's. Okay. So these are the orbitals, and we're saying that our model, the rope model, matches this perfectly. Balloons, that's what you're staring at. And those are the different shapes of the balloons. The more balloons you put in there, they have less room to do like a circular one, a spherical one like the S or orbitals, and they have to have these other strange shapes. Okay, and so we're saying this is perfectly for the rope model. Yeah, what we've been looking at all these years in that little tiny world are balloons. Okay, they're not orbitals. Orbital is a concept, so is an energy level. Those are concepts. And they say, well, it's where you can find the electron bead. No, the electron's not a bead, because if it's a bead, you can't do anything with it, because how are you going to explain action at a distance? You're going to have to introduce angels, spirits, or mathematical concepts, which is what they've done. They've introduced, field, time, energy, force, and so on. Okay, so here we have the orbiting bead again, okay, just in case. So when we look at these orbitals, they say it's mediated by an atom like that. And so this clown that was trying to tell us that, orbitals map perfectly well with what we get out of the atomic force microscope. Absolutely not. What we're seeing there is a ball, and what we're seeing here is a little ball that's going around another one. And that's not what you see there. That's not what the atomic force maps. Okay, so let's make sure that's absolutely clear. Okay, so what happens when you rub plastic? Well, you rub plastic, and now you can pick up all these papers, or you comb your hair, and you can pick up paper. There's what they call static electricity. How do we explain it? They explain it by saying they left the electrons, or pulled out the electrons, depending on which of the two objects you're talking about. One becomes negatively charged, the other one positively charged. And now because one is positive, the other one is negative, we all know that positive attracts negative, women attract men, sometimes. And they come together. There's attraction. We have pull, okay? How do they explain pull? We have no explanation. It's just black magic. How do we do it with the rope model? Well, we have these threads going around, as I just explained, ionic bond, right? So if they're both going in the same direction, the threads that are spinning around the atom that has been stimulated and has released some threads, and that these threads are going around, one comes down, the other one comes up, and now you have an attachment. And I'm saying that's what's happening with plastic. When you rub plastic, you're stimulating the atoms. They're twirling around at great speeds, right? Releasing a few, maybe one, but I think it's more than one. I think they're releasing a few of the threads, not rows, threads around. They're spinning around the atom, and they're coming up with the atoms of the paper, or perhaps the entire paper. Maybe it's just sweeping the paper up, because remember the, strength of a static electricity is not very strong, not like a magnet. A magnet can attract things much more, stronger. You can see it here. I don't think you can do that with static electricity this strong, right? And then the question is, well, if the threads are spinning around, several of them, and you have a magnet, why doesn't a magnet attract the plastic? Okay, because you have, the spinning of the threads in a magnet, and you have the spinning of the threads in a plastic, which is amorphous, right? See, you have this situation. You have in magnets, you have domains, right? And when you align them, like you see at the bottom, right? All the atoms are pointed in the same direction, or spinning. Their threads are spinning in the same direction. So you have all these groups of atoms, including the domains themselves, right? And they're all contributing one to the other to pull. You have gazillions of threads going in the same direction. That's not the situation you have with amorphous materials such as, for example, plastic, right? Could have also with glass happens as well. They're amorphous. And that means that the atoms that form the molecules themselves, they have their threads spinning in all kinds of directions. They don't have domains where you can align them all in the same direction, for otherwise you would have a strong magnetic field. What you have is the threads going in different directions, and that's why it's much weaker than the ones produced by a magnet. And so what's the issue? The issue there is, first, that explains why the magnet does not attract plastic, because it's not, you don't have what another magnet would have, which is going in the same direction, all the threads going in the same direction. Here you have them all going in different directions, but remember the threads extend far out from the plastic, and they are able to catch, the paper on your table. And but you have to be kind of close for them to do that. You can't do it from out here. It's not that strong. And again, it's not that strong because they're not aligned. So you have, all these threads spinning around because you've stimulated the atoms, right? And so now they're spinning around and they're pulling them up. Okay, they're pulling all these atoms up, and they don't interact. The threads from a plastic do not interact with a magnet because, again, they're all going in different directions. And a magnet has no way of attracting something that has all these threads going in different directions. Okay, so the threads are stimulated out of their atoms. They're spinning around, but they're all going in different direction. In a magnet, they're all going in the same direction because the domains are aligned.